I now want to discuss with you what we call in physics dimensional analysis. I want to ask myself the question, if I drop an apple from a certain height and I change that height, what will happen with the time for the apple to fall? Well, I drop the apple from at height h, and I want to know what happens with the time when it falls. And I change h. So I said to myself, well, the time that it takes must be proportional to the height to some power alpha. Completely reasonable. If I make the height larger, we all know that it takes longer for the apple to fall. So that's a safe thing. I said to myself, well, if the apple has a mass m, it probably is also proportional to the mass of that apple to the power beta. I said to myself, gee, yeah, if something is more massive, it will probably take less time. So maybe m to some power beta. I don't know alpha, I don't know beta. And then I said, yeah, there is also something like gravity. There is the Earth's gravitational pull, the gravitational acceleration of the Earth. So let's introduce that too, and let's assume that that time is also proportional to the gravitational acceleration. This is an acceleration. We'll learn a lot more about that, to the power gamma. Having said this, we can now do what's called in physics a dimensional analysis. On the left, we have a time. And if we have on the left side a time, on the right side, we must also have time. You cannot have coconuts on one side and oranges on the other. You cannot have seconds on one side and meters per second on the other. So the dimensions left and right have to be the same. What is the dimension here? That is t to the power 1. It's that t. That must be the same as length to the power alpha times mass to the power beta times acceleration. Remember, it is still there on the blackboard, has dimension L divided by time squared, and the whole thing to the power gamma. So I have a gamma here, I have a gamma there. This side must have the same dimension as that side. That is non-negotiable in physics. Okay, there we go. There is no m here, there is only one m here, so beta must be 0. There is here L to the power alpha, L to the power gamma. There is no L here, so L must disappear. So alpha plus gamma must be 0. There is t to the power 1 here, and there is here t to the power minus 2 gamma. It's minus because it's downstairs. So 1 must be equal to minus 2 gamma. That means gamma must be minus 1/2. But if gamma is minus 1/2, then alpha equals plus 1/2. End of my dimensional analysis. I therefore conclude that the time that it takes for an object to fall equals some constant, which I do not know, but that constant has no dimension. I don't know what it is, times the square root of h divided by g. Beta is 0, there is no mass. H to the power 1/2, you see that here, and g to the power minus 1/2. This is proportional to the square root of h, because g is a given and c is a given, even though I don't know c. I make no pretense that I can predict how long it will take for the apple to fall. All I'm saying is I can compare two different heights. I can drop an apple from 8 meters and another one from 2 meters, and the one from 8 meters will take 2 times longer than the one from 2 meters. The square root of 8 to 2, 4 over 2 will take 2 times longer, right? If I drop one from 8 meters and I drop another one from 2 meters, then the difference in time will be the square root of the ratio that will be twice as long.